Hello everyone, my name is Lancelot Grafilo and I'm here to discuss the processor management.
Now let's begin our discussion. First, I would like to introduce the flow of our discussion. Introduction, job scheduling versus process scheduling, process scheduler, process identification, process status, process state, accounting, process scheduling policies, process scheduling algorithms, cache memory, interrupts. What is processor management? In simple terms, refers to the coordination and control of a computer's central processing unit (CPU). It involves the efficient allocation of the CPU's resources to various tasks and programs running on the computer. This management ensures that each program gets the necessary processing time and resources to execute its instructions, preventing one program from monopolizing the CPU and slowing down others. Processor management is a crucial aspect of operating systems, as it helps maintain overall system performance and responsiveness by juggling multiple tasks effectively. So imagine the processor management is like a traffic enforcer directing cars at an intersection. The enforcer, which is the processor, ensures a smooth flow of traffic by deciding which car the task get to go next, preventing gridlock and keeping things moving efficiently. How does processor manager allocate CPUs to jobs? The process manager performs job scheduling, process scheduling, and interrupt management. Imagine the processor manager as a traffic enforcer of your computer. Its job is to decide which job or your task, like running a program, gets to use the CPU at any given time. In single-user systems, processor is busy only when user is executing a job. At all other times, it is idle. Processor management is simple. In multi-programming environment, processor must be allocated to each job in a fair and efficient manner, across a scheduling policy and a scheduling algorithm. Imagine the multi-programming environment is like a juggler managing multiple balls at once. Some important terms. A program is an inactive unit, such as a file stored on a disk. To an operating system, a program or job is a unit of work that has been submitted by a user. Job is usually associated with batch systems. Process or task, active entity, which requires a set of resources, including a processor and special registers, to perform its function. A single instance of an executable program. Thread of control. A portion of a process that can run independently. The thread of control refers to the sequence of instructions that a particular thread is currently executing. It's the path or flow of execution within that thread. Processor, CPU, or central processing unit, part of machine that performs calculation and executes program. Also, the processor is the brain of the computer. Multi-programming requires that the processor be allocated to each job or to each process for a period of time and deallocated at an appropriate moment. The processor manager has two sub-managers, which is job scheduler and process scheduler. The job scheduler is in charge of job scheduling, while the process scheduler is in charge of process scheduling. Job scheduler. High-level scheduler selects job from a queue of incoming jobs, places them in process queue, batch or interactive, based on each job's characteristics. Goal is to put jobs in a sequence that uses all systems resources as fully as possible. It strives for balanced mix of jobs with large I/O or input-output interaction and jobs with lots of computation. Tries to keep most system components busy most of the time. So imagine the job scheduler is like a personal assistant for your computer, helping it manage and organize tasks efficiently. A job scheduler handles a computer's tasks or jobs. The process scheduler is a low-level scheduler, assigns the CPU to execute processes of those jobs placed on ready queue by job scheduler. After a job has been placed on the ready queue by job scheduler, the process scheduler that takes over determines which job will get CPU, when or for how long, decides when processing should be interrupted, determines queue's job should be moved to during execution, recognizes when a job has concluded and should be terminated. Imagine a process scheduler is like the traffic director of your computer, deciding which programs or processes get to use the CPU and when. It's in charge of execution order of different tasks running in the system. Picture it as a conductor orchestrating a symphony, coordinating the flow of processes to keep things running smoothly. The process scheduler ensures fair access to the CPU, manages priorities, and handles the transition between different tasks, making sure your computer running everything is smoothly or efficiently. And now I will give the microphone to my fellow groupmates.
CPU cycles and input-output cycles. To schedule CPU, process scheduler uses common trait among most computer programs. They alternate between CPU cycles and input-output cycles. Poisson distribution curve. Input-output bound jobs, such as printing a series of documents, have many brief CPU cycles and long input-output cycles. CPU bound jobs, or such as finding the first 300 prime numbers, have long CPU cycles and shorter input-output cycles. Total effect of all CPU cycles from both input-output bound and CPU bound jobs approximate a Poisson distribution curve. Processor Manager, Middle-Level Scheduler. In a highly interactive environment, there is a third layer called Middle-Level Scheduler. Removes active jobs from memory to reduce degree of multi-programming and allows job to completed faster. So, kapag ang system ay nag-overload, doon na papasok ang middle-level scheduling. Siya yung aalis ng ibang active jobs sa memory in order to lessen the multi-programming so that the other jobs ay mabilis siya matapos. Job and process status. The job and process status, right from when it's created until it's terminated, after execution, it goes through various states. We are going to study these states and why the process transits from one state to another. There are 5 states a job takes as it moves through the system. There are hold, ready, waiting, running, and finish. Hold. When a process is just created, it is present in this state. For example, when you write a program and save it, it is started in hard disk, that is secondary memory. When we execute the program of operating, just picks it up from the secondary memory to place it in main memory. At that time, when it's just picked up to get a place in main memory, that is RAM. When we say that process is created and that state is the new state or the hold state. And when it's created, it becomes complete or ready. It then transits to ready state. We can say the process is in ready state when it enters the main memory or RAM and it's ready for execution. This state is the ready state. Process waits in ready state until CPU is assigned to it for execution. Many processes can be present in ready state or ready queue, waiting for their execution. Now, after waiting for some time in ready queue, the process will be scheduled for execution. The CPU will start executing the process. When the CPU starts executing the process at the time, process transits to the running state, where the CPU executes process. CPU will execute line by line. The executable code, now, again, it can go back to the ready state from running state. Now, let us see our process is getting executed by the CPU. And a high priority process comes in main memory or ready queue. As we have seen, CPU will give importance to high priority process, so it will stop executing our process and start the execution. The execution of high priority process. Our process will get preempted. That means it will be forced, stop, and it will go back to the ready state. Or, as we have seen in time sharing operating system, a process is executed for particular time quantum. Then, next process is executed. In that case, also process can go to ready state. From running state and wait in ready state for its turn execution. Another thing in process is in running state, it can require some input-output operation or some other event. CPU cannot wait till the time. So, the CPU stops the execution and process goes in waiting or block state. When it will complete the input-output operation or other required event, here also there is a waiting queue where multiple processes are present. Processes that are in waiting queue or present in main memory only after completing required operation directly cannot go to running state. It has to go to the ready state where again it will get scheduled for execution. Another thing can happen in running states is CPU will completely execute the process. It will execute the complete executable code. Process will get out of the main memory. Then the process will get completed and transit to the termination or finish state. Termination state, the process structure will get deleted as well as the process control block will get deleted and process will get terminated or finished by a prepping system. The process transitions are represented by arrows in a process state diagram, which shows the possible states and transition of process. For example, a process can transition from ready to running when the scheduler selects it from execution, or from running to waiting when it requests an input or output operation. Transition among process states. Hold to ready, job scheduler using a predefined policy. Ready to running, process scheduler using some predefined algorithm. Running back to ready, process scheduler according to some predefined time limit or other criterion. Running to waiting, process scheduler and it's initiated by an instruction in the job. Waiting to ready, process scheduler and is initiated by signal from input-output device manager that input and output device has been satisfied and job can continue. Running to finished, process scheduler or job scheduler.
Good day everyone. I'm JESSA MONEño. So I will discuss process control block or PCB, which is data structure that contains basic info about the job. So process control block, it is a data structure used by operating system to store and manage information about a running process. PCB contains important details about the process, such as its process ID, state, priority, register values, memory allocation, and other relevant information. So, process identification. When it comes, process identification refers to the unique identification assigned to each process running in an operating system. Next is process status, which include hold, ready, running, waiting. When it comes process status, it refers to the current state of a process in an operating system. There are several commonly used process states, which includes the hold, ready, running, and waiting. When it comes hold, this is a state that a process is temporarily suspended or put on hold. Ready. In the ready state naman, is a process that is waiting to be assigned to a CPU for execution. Running. When a process is in the running state, it is currently being executed by the CPU. And the last is waiting. The waiting state indicates that a process is waiting for an event or resource to become available. Next is process state. So process state, it refers to the current condition or status of a process in an operating system, which include the process status word, which is a data structure used by operating system to keep track of the current state of a process. Next is register contents, refers to the data stored in the registers of a computer's central processing unit or the CPU. Main memory info. It is used to store data in structures that are actively being used by the CPU during program execution. Next is the resources. When it comes resources, refers to the various assets or components that are required by a system, program, or process to function properly. And the last is process priority. Refers to the level of importance assigned to a process by the operating system. And the next is counting, which includes CPU time, total amount of time, input-output operations, number input records read, or etc. When it comes, accounting refers to the process of tracking and monitoring resource usage and system activities within a computer system or network. The next is PCBs and queuing. So, PCB of job created when job scheduler accepts it, updated as jobs goes from beginning to terminations. So when it comes to job scheduler, it's also known as a batch schedule or workload scheduler. It's a software tool or component that manages and schedules the execution of jobs or tasks in a computer system or network. So queues use PCBs to track jobs. PCBs, not jobs, are linked to from queues. Example, PCBs for every ready job are linked on ready queuing. All PCBs for jobs just entering system are linked on hold queuing. Queues must be managed by process scheduling policies and algorithms. So with queuing, when it comes queuing, it refers to the process of organization and managing a sequence of the items or tasks in a specific order, typically in a first in, first out or the FIFO manner. The next is process scheduling policies. So when it comes, process scheduling policies refers to the strategies and algorithms used by an operating system to determine the order in which processes are executed on a computer's CPU. So before operating system can schedule all jobs in a multi-programming environment, it must resolve three limitations of systems, which is a finite number of resources such as disk drives, printers, and tape drives. Some resources can't be shared once they are allocated, such as printers. And the last, some resources require operator intervention, such as tape drives. And the next is a good scheduling policy, which is a good scheduling policy refers to a process scheduling algorithm that effectively manages the execution of processes and optimizes the utilization of system resources. So, maximize throughput by running as many jobs as possible in a given amount of time. So, next is maximize CPU efficiency by giving CPU busy 100% of time. And the last, ensure fairness for all jobs by giving everyone an equal amount of CPU and input-output time. Also, continued by a good scheduling policy, which is minimize response time by quickly turning around interactive requests. And the next, minimize turnaround time by moving entire jobs in or out of system quickly. And thus, minimize waiting time by moving jobs out of ready queue as quickly as possible. So the next is interrupts. So when it comes to interrupts, an interrupt is a signal or event that occurs during the execution of a program, causing the normal flow of program execution to be temporarily suspended. It is a mechanism used by computer systems to handle and respond to various events that require immediate attention. So there are instances when a job claims for a very long time before issuing an I/O request, builds up ready queue and empties I/O queues, creates an acceptable imbalance in the system. Process scheduler uses a timing mechanism to periodically interrupt running processes when a predetermined slice of time has expired, suspends all activity on the current running job, and reschedules it into the ready queue. So the next is preemptive and non-preemptive scheduling policies. So when it comes to preemptive scheduling policies, refers to the process of scheduling algorithm that allow a running process to be interrupted or preempted by a higher priority process. So the operating system has the ability to forcibly stop the execution of a process and allocate the CPU to another process. So when it comes to preemptive scheduling, interrupts processing of a job and transfers the CPU to another job. So, nag-allocate siya or nag-interrupt, then I will transfer to the CPU or into another process. When it comes non-preemptive scheduling policy, it is also known as cooperative scheduling. Refers to the process scheduling algorithms where a running process cannot be interrupted or preempted by the operating system. Once the process starts executing, it continues until it voluntarily releases the CPU or completes its execution. So, the difference between preemptive and non-preemptive scheduling policies. So when it comes preemptive scheduling policies, it is allow for the interruption or preemption of a running process by the operating system, while non-preemptive scheduling policies is not allow for the interruption or preemption of a running process. So until it is issues an I/O request or natural wait or until it's finished exemption for infinite loops.
Everyone, here are the topic. It is all about process of scheduling algorithm. First is first come first serve. Second is shortest job next. The third is priority scheduling. Then the shortest remaining time. The first is the first come first serve. So, first come first serve is automatically execute the create process and request in the order of their arrival. And then, it is simple to implement and easy to understand. Then, it leads to convoy effect, low CPU utilization, and increased average waiting time. Then, it all depends on the position of processes in the FCFS key. So, kumbaga, ang advantage is easy to understand. And then, ang disadvantage naman is kapag bumaba ang CPU utilization ay lumalakas ang kanyang average waiting time. Then, nakadepende lang ito sa posisyon kung saan nakaprocess ang FCFS key. FCFS is implemented by using the FIFO key. So, ibig sabihin ng FIFO key is the first packet that arrives at a router is the first packet to be transmitted. Kumbaga, baga siya itong sa cellphone sa mga keypad na bar. Itong pag nag-charge ka, may guwasan galabas sa taas para makita mo kung pila na ang bars ang cellphone mo. Abe, itong pag isot pa lang, hindi pa na siya full. Tapos may gusto mga empty, amoy na itong empty battery. Ay free buffer gali. Pag empty, tapos pag puno na siya, full ang tawag sinada is key packet. Amoy na siya pag puno na ang bar. Try natin kung paano gumamit ng schedule process and FCFS algorithm gamit ang arrival time niya. Nakikita niyo yung P1 pa P5. Yan yung processes ng FCFS. Tapos sa base na is yung turnaround, yung may 0 to 15. Ito yung formula, P1 pa P5. So, kunin yung turnaround niya, yung sa baba niya, na 0 to 15, tapos minus niya siya sa burst time. Same lang siya nung sa process, pero number na lang, wala na yung letter P. Then, pag nakuha nyo na yung result ng burst time niya, compute nyo na lahat ng result, ipa-plus nyo lang at doon nyo na makukuha ang kanyang arrival time na millisecond. Then, divide nyo pa pala siya sa kanyang process na 5. Then, pag na-divide nyo na yan na yung milliseconds niya. The next is the shortest job next. This algorithm processes the length of the later next CPU burst when CPU is available. Then, select the waiting process with the smallest execution time to execute rest. Then, hindi rin siya practically implemented because burst time of a process can be predicted in advance. And ang shortest job next ay nagbibigay lang siya ng minimum na average to waiting time for a given at the process. Then, isa din siyang non-preempted. Priority scheduling. Easy to use. Then, one of the most common scheduling in batch system. Then, non-preempted. Easy to use kasi with a higher priority, execute first which save time. Kasi mahalaga lahat pag ang process ay precisely defend. Then, each process is assigned a priority. Tas kung highest priority naman, execute na agad siya una pa lang. Pero kung same lang din sila ng priority, naka-execute on a first come first serve basis na siya. Ito din yung formula ng priority. Iba siya dun sa una. Shortest remaining time is method that is a preemptive version of shortest job next. Then, since that the time should only use as execution process, either run until it completes or get preempted if a new process is added. So, parang mas mabilis yung shortest remaining time kesa dun sa shortest job next. Kasi new version na siya ng shortest job next. Tsaka magkaiba ito sa tatlo. Kasi preemptive ito at yung tatlo naman is non-preemptive. Then, examples and SRTF sa Gantt chart. Meron din siyang process tsaka brush time and arrival time lang yung hinahanap. Pero, pagdating dun sa result, hinahanap din nila yung millisecond. I-divide niya yung waiting time sa process. Then, pag nakuha nyo na, yun na yung milliseconds na kagaya din siya nung sa first come first serve. Pero iba lang yung kasi naka-Gantt chart yung shortest remaining. The last is context switching is required by all preemptive algorithm. All of its processing information must be saved in its PCB or printed circuit board are located in appropriate register. Kasi lahat ng process ng algorithm ay nasa circuit board lang makikita. Ito yung tinatawag nating circuit board.
So, hello everyone. Here we are at context switching is required by all preemptive algorithms. 1. When job A is preempted, all of its processing information must be saved in its PCB for later, or when job A's execution is continued. Context of job B's PCB are loaded into appropriate registers so it can start running again, or in this case, context switch. Next, later, when job A is once again assigned to a processor, another context switch is performed. Info from preempted job is stored in its PCB, and contents of job A's PCB are loaded into appropriate registers. And so, basically, why we need context switching is because it helps in storing the process state to resume yung mga task sa OS, which the process has to restart the execution sa simula ng levels in case an interrupt occurs when a process runs in an OS. The status of the process is saved sa register using context switching. So, round robin. Preemptive. Used extensively in interactive systems because of its easy to implement. Isn't based on job characteristics but on a predetermined slice of time that is given to each job. It ensures CPU is equally shared among all active processes and isn't monopolized by any one job. So, si round robin, siya raw yung nag-determine and nag-make sure na naka-divide yung mga process at hindi lang sa isang CPU naka-focus yung isang trabaho. Time slice is called a time quantum. Size crucial to system performance.
100 ms, 100 ms to 1 to 2 seconds. So, yung time quantum is fixed and nakaschedule yung mga processes para no process can uh, get CPU time more than one time quantum in one go. If Jobs' CPU cycle time quantum. If Jobs' last CPU cycle and job is finished, then all resources allocated to it are released and completed job is returned to the user. So, pag daw yung last CPU cycle and the job is finished, then yung mga resources na naka-allocated dun ay i-release na. Tapos yung completed na job babalik na sa mismong user. If CPU cycle was interrupted by input-output request, then info about the job is saved in its PCB and it is linked at the end of the appropriate input-output queue. Later, when input-output request has been satisfied, it is returned to end of ready queue to wait allocation of CPU. So, if CPU cycle is interrupt by na-interrupt ng input-output na request, yung mga info sa job is masasave siya sa PCB at ililink to sa appropriate na input-output queue. At pag yung input-output request is naging okay na, ibabalik siya sa katapusan ng ready. Time slices should be 1. Long enough to allow 80% of CPU cycles to run to completion. And number 2, at least 100 times longer than time required to perform one context switch. And the last one, flexible, depends on the system. So, kailangan daw at 80% yung CPU cycle para matapos at makomplete yung process. And at least 100 times mas yung longer yung oras na kailangan para ma-execute yung context switch. And syempre flexible is pwede mo siyang ma-configure and nakadepende sa system. Multiple level queues, not a separate scheduling algorithm, works in conjunction with several other schemes where jobs can be grouped according to a common characteristics. So, ito daw ay nagwo-work sa several na schemes kung saan yung mga jobs pwedeng i-group sila according sa pagkakatulad ng mga characteristics nila based sa level of queues. The examples of these are the following. Priority-based system with different queues for each priority level. So one of the example for this is that this is a priority system based on other queues that are dependent on the priority level of their own. Next is put all CPU-bound jobs in one queue and all input-output bound jobs in another. Alternately, select job from each queue to keep system balanced. So this puts the CPU to only one queue where it focuses and the other input-output bound jobs to the other process. And it on also It can also choose other specific jobs to the queues so that it can make the system more balanced. The last is put batch jobs, background queue, and interactive jobs in a foreground queue. Treat foreground queue more favorably than background queue. So this makes those jobs to put them in the foreground queue, which is uh which which has the background and interactive jobs, and it treats them and focuses them more than the background. So here are the 4 policies to service multi-level queues. First is no movement between queues. Second, move jobs from queue to queue. And third, move jobs from queue to queue and increasing time quantums for lower queues. So for the lower queues, we should um, move jobs in the queue to queue and increase its time quantums. Last is give special treatment to jobs that have been in system for a long time, called aging. So it says here that we should focus more on other jobs that is that that have been inside the system for some time.
Cache memory. I want to share a little information about cache memory. Cache memory is a chip-based computer component that makes retrieving data from the computer's memory more efficient. And cache memory is a quickly accessible memory that is designed to alleviate the speed difference between a very fast CPU and a slower main memory. So imagine like it's a balancer between the two. Furthermore, the cache memory stores copy of frequently used data in an easily accessible memory area instead of main memory. In addition, it acts as a temporary storage area that the computer's processor can retrieve data from easily. Now let's take a look at this diagram. When the CPU needs data, it sends a request to the cache controller. If the needed data is already in the cache a heap, the cache controller sends it to the CPU. If it's a hit, data is in the cache. The data goes from the cache to the CPU. If it is a miss, data is not in the cache. The cache controller fetches the data from the main memory. In summary, from CPU to cache controller, the CPU asks for data. From cache controller to cache memory or main memory, decides based on whether the data is in the cache, hit or not, miss. From cache memory or main memory back to the CPU, sends the data back to the CPU, either from the cache or after fetching from the main memory. This process helps speed up the CPU by storing frequently used data in the faster cache memory and fetching less frequently used data from the larger but slower main memory when needed. Types of interrupts. The first one is the page interrupts to accommodate job requests. The second one is the phantom expiration. Input-output interrupts when issue read or write command. Internal interrupts. Synchronous interrupts result from arithmetic operation or job instruction currently being processed. Illegal arithmetic operations, such as divided by zero. Illegal job instruction, for example, attempts to access protected storage locations. Now let's go to the interrupt handler. It is to describe and store type of interrupt passed to user as an error message. Save state of interrupt process. value of program counter, mode specification, and contents of all registers. How to process the interrupt. First step is send error message and state of interrupted process to the user. Next is hold program execution. The next one is release. Any resources allocated to job are released. Job exits the system. And the last one is processor resumes normal operations. And that's all for Processor Management Chapter 4, Group 2. Thank you everyone, and God bless.